Now, in the previous workbooks, you've learned to calculate the masses of reactants and products using reaction stoichiometry. You've also learned the mathematical relationship between pressure, volume, temperature, and amount in moles of gases. And the ideal gas equation is derived from the gas laws. In this workbook, you'll learn to calculate the volumes of gases consumed or produced in a chemical reaction using stoichiometry and the gas laws. Now, there are two laws that we will follow in this workbook. One is Gay-Lussac's law of combining volumes. Gases combine with each other in simple proportions by volume. So there are some numerical problems relating to this. And the second is Avogadro's law, which says equal volumes of all gases when measured at the same temperature and pressure contain an equal number of particles. An extension of Avogadro law is that at standard temperature and pressure, temperature is 273 Kelvin, pressure is 100 kilopascals, 1 mole of a gas occupies 22.7 decimeter cube volume. Now let us see some examples where we can apply these laws. Here is a chemical reaction in which all the reactants and products are in the gaseous state, and therefore we can apply Gay-Lussac's law of combining volumes. And here you can see in molar ratio it is 1:3:2, but the volume ratio also remains the same. That is, 1 volume of nitrogen will react with 3 volumes of hydrogen to give 2 volumes of ammonia. Now, when we say volume, that means the unit could be either in centimeter cube, decimeter cube, or meter cube. Say, for example, 100 centimeter cube of nitrogen will react with 300 centimeter cube of hydrogen to give you 200 centimeter cube of ammonia. So if you have 4.5 decimeter cube, how much hydrogen would be required to completely react with the nitrogen? So the given quantity is 4.5 decimeter cube of nitrogen. The required quantity is volume of hydrogen. A and B represent the stoichiometric coefficients of given and required quantities, which in this case indicate the volume ratio. Now, the volume ratio is 1:3, and we can calculate the volume of hydrogen using 4.5 decimeter cube, which is given in the problem. And that is going to be 3 times 4.5 over 1, which is 13.5 decimeter cube. And this is how you can apply Gay-Lussac's law of combining volume. Now, here's another example where we calculate volumes of gases using ideal gas law and Avogadro law. In this question, sodium azide decomposes to give sodium and nitrogen, and you would notice that sodium azide is in its solid state, sodium in solid state, but nitrogen is in the gaseous state. And you have to calculate the volume of nitrogen gas formed, measured at 298 Kelvin and 110 kilopascal pressure, when 10 grams of sodium azide decomposes. So as always, it's very important to identify what is the given quantity and what is required. So in this case, the mass of sodium azide, which is decomposing, is 10 grams. And the required quantity is the volume of nitrogen gas released. Now, the first step would be to convert the given quantity in amount in moles. So that would be 10 divided by the molar mass of sodium azide, which is 65.02, and you have 0.154 moles. Now this is rounded to 3 decimal place. Now in the workbook, answers to some intermediate steps are rounded up, but it will make little or no difference in the final answer. A and B is the stoichiometric coefficient between the given and required quantities, and in this case it is 2:3. And so A is 2, B is 3, amount in moles of the given quantity is 0.154. So therefore the required quantity, that is nitrogen gas, would be 3 times 0.154 divided by 2, which is 0.231 mole. So now you know so many moles of nitrogen are released, but we've got to do one more step, and that is to convert 0.231 moles into volume of nitrogen gas. So we use the ideal gas equation here. So V is the volume of nitrogen gas. You already know N, which is 0.231. R is 8.31. Temperature has to be in Kelvin scale. Pressure has to be in kilopascals. Then your volume would be in decimeter cube. And in this case, it is 5.2 decimeter cube. And if required, you can convert this into centimeter cube by multiplying it by 1,000. So that depends on the question. And in this case, you can convert this into 5,200 centimeter cube. So there are 10 such questions. So good luck and enjoy.